Okay, so welcome to the Tutte Colloquium. We're very happy to have Huang here to give a talk. So Hao graduated from UCLA in 2012, and then he did a few postdoc positions in Rutgers, Princeton, and also University of Minnesota before joining Emory University. So Hao had a lot of contributions to extremal combinatorics, and in particular, he solved the long-standing sensitivity conjecture in 2019, I think. So we're very happy that he's here today, and we'll talk about interlacing methods in extremal combinatorics. So welcome.
Thanks, Glenn, for the introduction, also for the invitation to give a talk in this Tutte Colloquium. So it's my great pleasure being here. So I think I actually did a physical visit to Waterloo in 2013, and that sounds like a long time ago. So today I'm going to talk about the application of interlacing method in extremal combinatorics. So like many other talks in this field, I will start with the Erdős-Corrado theorem. So it's often considered as the cornerstone of modern combinatorics. So I think actually it was in the 30s, but the paper was published in the 60s. So Erdős and Corrado showed that if you have an intersecting family of a subset of an n element set, then as long as n is greater or equal to 2 times k, then this family has at most n minus 1 times k minus 1 subset. So here, when I talk about intersecting family, I just mean that if you take any two subsets from this family, then they have a non-empty intersection. So where does this upper bound n minus 1 to k minus 1 come from? You just fix one element, and then you take all the k subsets containing that fixed element. So that gives you n minus 1 to k minus 1. And as you can probably see that if n is less than 2k, then you can just take every k set. So that's the best example for that range. So there are many different proofs of this Erdős-Corrado theorem. So you can, for example, use the induction and some shifting arguments. Or the most famous proof is probably Cartonnas's circle method using the probabilistic technique. And actually there are two different proofs using the spectral method. And I'm going to talk about this briefly today. So the way to use spectral graph theory to prove a extremal combinatorial result like Erdős-Corrado theorem usually is by formulating this into a graph independence number problem. So for example, you can construct the so-called Kneser graph, Kg of nk. So there are two parameters, n and k. So both are integers, n is greater than k. And you just put all the k subsets as the vertices of the Kneser graph. And you put an edge between two k subsets if they are disjoint. So for example, you can add an edge between 1, 2, and 3, 4, and 1, 2, and 4, 5, 1, 2, and 3, 5. So now the independence number of this huge n to k vertex graph is exactly what we're looking for, right? Because what's the independence set in this huge graph? It's exactly an intersecting family. If you want to find the largest intersecting family, that means you want to find the independence number of this huge graph. So in this example I show you, this is a famous Peterson graph, and on the other hand is the Kneser graph, Kg of 5, 2. And we all know that the independence number is equal to 4. These are the 4 vertices circled in red. Okay, so how do we study the independence number of a huge but highly symmetric graph? So there's one very useful technique called interlacing. So in particular, I think the name comes from the Cauchy's interlacing theorem. So if you have a symmetric m by n matrix A, and you have a smaller principal submatrix of A, let me call this B, of size, let's say m by m, and m is less than n. Now suppose, okay, so we know that for symmetric matrices, all the eigenvalues are real numbers. So you can sort them in descending order. So for example, all the eigenvalues of A, you call it lambda I, and eigenvalues of B are called mu j. Then it turns out that if you take the i's largest eigenvalue of A, this is greater or equal to the i's largest eigenvalue of B. And if you take the j's smallest eigenvalue of B, is greater or equal to the j's smallest eigenvalue of A. Okay. And how do you prove such a result? So if you are familiar with the min-max principle in the matrix theory, so basically the i's largest eigenvalue can be given by a formula involving the maximum of a minimum of the Rayleigh quotient, or it's the minimum of the maximum of a Rayleigh quotient. So I don't plan to elaborate on that. But basically, you can just take this min-max principle and it immediately implies Cauchy's interlacing theorem. And if you are not happy with such happy machinery, you can take a look at a proof by Steve Weeks using polynomial interlacing. And that, I mean, if you assume some results in polynomial interlacing, then this Cauchy's interlace theorem just follows by a one paragraph. Okay, so from now I just take it for granted and show you some applications in small combinatorics. So there are two immediate upper bound or independence number you can obtain from this Cauchy's interlace theorem. So for example, if you take a graph G, an undirected simple graph G, and you consider its adjacency matrix AG. So what's AG? So it's an n by n matrix, and you put entry 1 if I and j are adjacent. You put entry 0 if they are not adjacent. Now the independence number of your undirected graph is bounded from above by both the number of non-negative eigenvalues of its adjacency matrix and the number of non-positive eigenvalues of the adjacency matrix. So how do you see this from Cauchy's interlace theorem? So you just take the adjacency matrix of G and you look at the largest independent set. So this has to be a alpha by alpha or 0 principal submatrix. So now you can just call this matrix B and you apply Cauchy's interlace theorem. So what are the eigenvalues of an all-0 matrix? So you know that there are alpha eigenvalues and all of them are 0. And we don't know what the eigenvalues of the larger matrix are, but let me just write them in descending order. So now we know that the alpha's largest eigenvalue, lambda alpha, has to be greater or equal to mu alpha, which is greater or equal to 0. So that at least alpha non-negative eigenvalues among lambda I. And similarly, you can show that at least alpha non-positive eigenvalues among those lambda I. And that gives you this type of upper bound. So it's time for some very interesting family of graphs, including the Kneser graph, as we will see in a moment. And there's another bound called the ratio bound of attributed to different people. So if you have a regular undirected simple graph, let's say the degree is d, then you know the largest eigenvalue is equal to d as well. Then the independence number is bounded from above by n times the absolute value of the smallest eigenvalue divided by the difference between the largest and the smallest eigenvalue. And so if you go back one slide, so for Cauchy's interlace theorem, it's actually true in a more general sense. So you can, it's true if you have this matrix B equals P transpose times A times P. And P is a so-called projection matrix in the sense that P transpose times P is equal to an identity matrix, which is, so P doesn't have to be a square matrix. So M could be smaller than N. So if P satisfies these properties, then the eigenvalues of B and eigenvalues of A interlace, meaning that they satisfy the same type of inequality. Okay. And if you find a proper P, then you can use this to prove the so-called ratio bound. So you, instead of bounding this by the multiplicities of non-negative and non-positive eigenvalues, you bound this by certain ratio. Okay, so why do people consider this type of upper bounds on the independence number? Because it's useful for proving some results in small combinatorics. So one particular example is if you just apply these two bounds directly on Kneser graphs, then you can prove this Corrado theorem in two different ways. So here I'm not going to do linear algebra calculation, but it's quite well known that we can determine the eigenvalues and eigenvectors of the adjacency matrix of the Kneser graph. So there are k plus 1 different eigenvalues, and the multiplicities are given by the difference between two consecutive binomial coefficients. So they add up to n to k. And the signs are alternating. So from here, if you apply both the ratio bound and the inertial bound and do some calculations carefully, you get n minus 1 to k minus 1 in both cases. And actually, one thing I did not mention earlier is both bounds work for something called a pseudo adjacency matrix. So in the sense that you can take any matrix M, such that this is symmetric. And if two vertices are not adjacent, you put 0. If they are adjacent, you can put an arbitrary number. This could be 0, or this could be some positive or even negative numbers. And for the inertial bound to hold, you just do the same proof. And so you can pick this, you can basically change the one entries of the adjacency matrix to anything you want, just to make sure that this is a symmetric matrix. And for the ratio bound, you have to be a bit careful because you want to maintain some kind of regularity. But if you do this more carefully, you can eventually get to the robust theta number. Okay, so I just showed you two the Erdős-Corrado theorem, but is that all? No. So actually, there's a degree version of Erdős-Corrado we can prove using the spectral method. And if you want, you can sort of formulate the proof using the interlacing language. So with each in 2017, so we were first considering some problem about so if you have a k-uniform hypergraph, what are the minimum degree that guarantees you a matching of certain size? And we have worked on that type of problem for a while, and then we realized even the simplest case, we don't know how to prove it. So for example, if you have a k-regular n-vertex hypergraph, so every edge is a subset of size k. So you can also view this as a family of k subset of an n-element set. So suppose you want to find the minimum degree of this hypergraph that guarantees you a matching of size 2. So this is exactly the following question. So if you have an intersecting family of this subset, so what's the, so if you consider the least popular element in your ground set, how many times it has to be contained in this fact? So in the beginning, we saw that this must be well known in the literature, but then we could not find it. It took us some time to prove it. But in the end, we are able to show that if n is greater or equal to 2k plus 1, and this is an intersecting family, then there exists an element contained at most n minus 2 to k minus 2 subset from your intersecting family. So first of all, this bound n minus 2 to k minus 2 is struck, just like the n minus 1 to k minus 1 bound in Erdős-Corrado theorem. Because you can similarly fix one element and take all the k subset containing the element. So this fixed element is the most popular element in the ground set. So it appears n choose k times. So n minus 1 choose k minus 1 times. And for the remaining element, each appears n minus 2 choose k minus 2 times. So our result is that there must exist a least popular element contain at most n minus 2 choose k minus 2 subset. And this bound is also best possible in the sense that you cannot replace n greater or equal to 2k plus 2 to anything below that. I mean, we have some examples. So why this degree version of Erdős-Corrado theorem is interesting? Because it actually implies the original Erdős-Corrado, right? Because if you assume that your n is greater or equal to 2k plus 1, so that means you have the least popular element, let's say this 1. So you delete at most n minus 2 to k minus 2 subsets containing this element. So you end up with at most, at least, so I mean, so basically every time you just peel off one vertex, and when you arrive at the case when n is equal to 2 times k, you can just do some counting easily. So basically combine induction and this theorem, so you can prove the Erdős-Corrado theorem. In some sense, it's stronger than the EKR. And so you might wonder what I mean by this picture here. So basically, after you apply the spectral method, the proof can be reduced to showing that if you have a bunch of vectors, they pairwise form the same angle in the d-dimensional space, and they're d plus 1 vectors. So for example, when d is equal to 2, so you have these 3 vectors each. So their pairwise angle is equal to 120 degrees. Then no matter which vector v you choose, there exists one of these 3 vectors such that the angle between this ui and v is greater or equal to 120. Okay, but I have to prove a higher dimensional analog of that. And now we come to a very natural question. So here we deal with the 1 degree. So basically you consider the least popular element. And can we prove that for example, the least popular D tuple is contained in at most n minus D minus 1 choose K minus D minus 1 subsets of your intersecting family. So is it even true that this was for n greater or equal to 2k plus 1 or 2k plus c for some small constant c? I don't think this is no, and we try very hard to get this type of result, but it looks like there's some limitations, at least for the method that we are aware of. And Kupowski used a combinatorial technique and proved this for n greater or equal to 2k plus 3d over 1 minus d over k. So I think I have to be careful with this term here. So I just want to pause for a moment to see if there's any questions. So if not, let me jump to a somewhat different topic. So we all know one of the most famous results in mathematics, the Isoparmature Inequality. So roughly speaking, it says that if you have a closed curve on the plane, then the region it encloses has an area that is at most L squared over 4 times pi, where L is the length of this closed curve. So I think people know this type of result, I think as early as the time of ancient Greece, I guess. So according to Homer, this Queen Dido escaped from Europe to the North African coast. And so basically she gave us some of her treasures, and in return, she could get the land that can be sort of enclosed by a single ox hide. And of course, she was very smart, much smarter than a lot of mathematicians. So she asked her companions to cut this ox hide into some smaller pieces and tie them into a long strip. And then they used the natural boundary of the North African coast together with this very long strip to form the future Carthage. Okay. Although people know this type of result for a long time, but I think the first mathematically rigorous proof of the Isoparmature inequality was only obtained in the late 19th century. So today I'm going to talk about a slightly less well-known inequality called the Isothermatic Equation. So if you look at the previous result, so basically we look at the perimeter versus the area, or if you look at the higher dimensional case, it's like the surface area versus the volume. Now what happens if you replace the perimeter by the diameter of your set? So the diameter of a set is just defined as the maximum distance between 2 points of your set. Now, suppose your set behaves nice enough as a subset of the n-dimensional Euclidean space. So you can essentially prove the same result. So the ball maximizes the volume among all the such nice sets with equal diameter. So this is what the Isothermatic inequality is about. So for mathematically rigorous proof, you can apply something called the Steiner symmetrization. So basically you replace S by S minus S over 2. And then you can apply the Minkowski inequality to prove this such inequality. But of course, the difficult part was hidden in this proof of Minkowski. Okay, so this is for the continuous case. Now what happens for the discrete case? So one natural discrete object to consider is the n-dimensional hypercube. And if you look at all the n-dimensional 0, 1 vectors, you can define a Hamming distance between any pair of vectors. So for example, if you have 0, 0, 0, 0, and 1, 0, 1, 0, then the Hamming distance between them is equal to 2. So just count the number of coordinates they differ from. So you have 1 and 1 here. So this gives you a definition of a distance on the n-dimensional hypercube graph. And from the distance, you can define the diameter, which is just the maximum pairwise distance. And so now the question is, if you would like to prove an isothermatic inequality, what's the natural candidate for the volume? So I think it's somewhat natural that we can assign equal weight to every binary vectors. So every binary vector gets the weight of 1 over 2 to the n. So basically the volume is just 1 over 2 to the n times the number of vectors in your family. So in the 60s, Kleiman proved the following result. So if you take your favorite collection of binary vectors And you already know that the Hamming distance between any two vectors from this family is at most d. D is some fixed constant which is strictly smaller than n. N is the dimension of the hypercube. Then you know that F cannot contain more than a certain number of vectors. And this maximum is given by the largest Hamming law of radius d over 2. So if you view this binary vectors as subset, so basically you're taking n choose 0, union n choose 1, union n choose d over 2. So here, let me only talk about the even case. So if you take the indicating vectors of all the subsets of size up to d over 2, then their pairwise Hamming distance is at most twice of d over 2. That's at most d. And that's the best you can do. So, I mean, when d is odd, I mean, you can also view the extremal construction as some kind of Hamming ball, but I don't plan to, go over that. So in the original proof of climate, he actually used a somewhat complicated shifting technique. So it's very specific to this problem. And with two of my collaborators, Oleg Kluman and Cosmin Pohata, we were able to sort of show that the climate theory actually follows from spectral graph theory. So more specifically, we showed that there exists a pseudo. Okay, so maybe I should say it this way. So first of all, you reformulate this problem as the problem of finding the independence number of some large graph. And the number of vectors in this large graph is equal to 2 to the n. So every vertex corresponds to an n-dimensional binary vector. And the problem becomes an independence number problem. Then we can try to apply the inertia bound. But if you just take the usual adjacency matrix, it doesn't work. So you have to carefully choose a pseudo adjacency matrix. So basically, we show how to choose such a pseudo adjacency matrix so that inertia bound gives you exactly this sum of binomial coefficients. And the really nice thing about our proof is it actually applies to some other distance set. So for example, so previously you allow the distance between any two binary vectors to be between 1 and b. Now what happens if you just take other set? So this method usually gives you some bound. So it's not always tight, but sometimes you get some pretty sharp upper bounds. And here, let me very, very briefly sketch the proof. So as I said, so we try to convert this into bounding the independence number of a huge, very symmetric graph. So we define a graph G. So its vertices are just all the binary vectors, of dimension n. And you put an edge between two binary vectors if and only if their Hamming distance is strictly greater than the diameter. So here, for simplicity, let me just do it for even d. So assume that d is equal to 2 times d. The method also works for odd diameter, but you have to sort of modify a little bit. Okay, so now after you define this huge, highly symmetric graph, its independence number is exactly the maximum number of vectors you could have such that their pairwise distance is at most d. Now, how to bound the independence number? So we try to use the inertial bound, but to use the inertial bound, so let me remind you what this is. So alpha is less or equal to the number of positive, non-negative eigenvalues and the number of non-positive eigenvalues of not just the adjacency matrix, but any pseudo adjacency matrix. Okay, now the question is, how do we pick the pseudo adjacency matrix? So we only consider those matrices whose entry. So if you think of the rows and columns as this 0, 1 vectors, so we only consider those matrices such that the UV's entry is determined by f of the Hamming distance between U and V. So the benefit of only looking at those pseudo adjacency matrices is we can compute the eigenvalues very easily. So basically, such matrix can be written as a linear combination of the matrices M and K. So I did not define here, but you can probably guess what it is, right? So M and K has the UV's entry equal to 1 if and only if the Hamming distance between U and V is exactly equal to K. Okay, so the really nice property about this matrices is they all share the same eigenvectors. That means if your M is a linear combination of those matrices, then the eigenvalues of M is also a linear combination of the corresponding eigenvalues of those matrices. So here you can sort of do a little bit of computation, and it turns out that for those such pseudo-adjacency matrices M, the eigenvalues only have M plus 1 different values. I mean, at most M plus 1 different values. So, and lambda I has multiplicity n choose I. So the sum of n choose I is equal to 2 to the n. Now you just need to carefully pick f, this f of k, such that the signs of this eigenvalues lambda I behave very nicely. So it turns out that we can find such assignment of f, so that it gives you a pseudo-adjacency matrix. And on the other hand, if you compute all these eigenvalues, so it turns out that all the middle ones are greater than 0. And then the first t plus 1 eigenvalues are alternatively greater than 0 or less than 0. And then the remaining, I mean, the last maybe t or t plus 1 eigenvalues are also alternating, but in a different way. So for example, if you count the number of non-positive eigenvalues, then it's just lambda 1, lambda 3, lambda 5, and so on. And here you have lambda n minus 2, and so on. So if you add up all this gives you exactly n choose 0 plus n choose 1 plus n choose d over 2. That's how the proof works. But of course, I skipped the most non-trivial part of how to determine the values of f of k. So now we can't keep wondering whether there's how widely applicable this method is. So one problem that interests me a lot is this independence number of the orthogonality graph, which in some sense is very similar to the previous problem. So the orthogonality graph, omega of n, has the vertices that are n-dimensional plus minus 1 vectors. And 2 vectors are adjacent if and only if they are orthogonal. So for example, 1, 1, 1, 1, and 1, 1 minus 1 minus 1 are orthogonal. So you can also think of this, I mean, define this using the Hamming distance between these 2 vectors. You can probably formulate carefully. So I think the Hamming distance is equal to n over 2. Now there was this conjecture by Galiad, and I think also independent maybe by Franco. So what's that? They believe that the independence number is equal to the sum of certain binomial coefficients. And the reason I put n equals 4k here is because if n is odd, then I don't think you can find pairwise orthogonal vectors. And if n is of the form 4k plus 2, then you just get a bipartite graph with a perfect matching. So the independent number is just equal to half of the number of vertices. So that's trivial. But when n is divisible by 4, so you have a natural candidate for that possibly would maximize this independence set. I mean, the size of the independence set, but you don't know if that's optimal. So this is proved for some very interesting case when k is a power of prime, basically. So for odd prime, it was proved by Franco, and then very recently, I think 2 years ago, for even primes, I mean for even prime powers, it was solved by Illinger and Tanaka. So for both of the proof, I think essentially they use this type of inequality. So alpha of G is less or equal to the rank of some non-zero diagonal matrix plus a pseudo adjacency matrix. Okay, so why does that work? So if you have a pseudo adjacency matrix, that means the independent set corresponds to all zero principal submatrix. Now, if you add some non-zero elements to the diagonals, so these diagonal entries of this matrix become non-zero, and the rest are still 0. So this principal submatrix has full rank. But of course, the rank of the entire matrix should still be greater or equal to the rank of this matrix. And that's how you screw upper bound independent number. And the really nice thing is that this bound was over some finite field. No, there's no reason to only consider the rank of a matrix over the reals. And I think basically they picked some finite field, I think it's P, FP, and so that, and then just apply this carefully. Now, you see this is still open when n is equal to 4 times k, when k is some composite numbers. So the question we want to ask is, can we develop an inertial bound over finite fields? And maybe it has the potential of improving this upper bounds. So I don't know how to do that yet. Okay. So questions? Now I'm moving on to the third type of problems. And this is a so-called sensitivity conjecture. So it's also another application of this interlacing method. So previously, we only used this interlacing method to upper bound the size of the independent set in a very nice graph. But we can actually do a little bit more than that. So for example, if you take an induced subgraph, which is not super small, then maybe we can lower bound the maximum degree of the induced subgraph using this interlacing method. And this is just one such example. So let me briefly talk about the background of this conjecture. So in theoretical computer science, people study the so-called Boolean function. So basically it maps all the n-dimensional binary vectors to either 0 or 1. So it receives n bits of 0 and 1 and outputs just 1 bit. And for every Boolean function, we could just write as a unique multilinear real polynomial. So for example, if you take the n function, so it's basically you take x1 times xn. And if you take the OR function, then it's just 1 minus the product of 1 minus xi. So this real polynomial, for this real polynomial, we can consider this degree. And this is defined as the degree of this Boolean function. But of course, not every multilinear real polynomial gives you a Boolean function. Right? For example, if you take f equals x1 plus x2 over 2, then when you take x1 equals 0, x2 equals 1, that does not even give you 0 or 1. So there's only a small proportion of real multilinear real polynomials that represents a Boolean function. Now, in computer science, people study several different complexity measures of a Boolean function. So some of the most important ones include the sensitivity of a Boolean function. So to define the sensitivity, first we can try to define this locally. So if you fix the input x, then the sensitivity of this Boolean function f on the input x is just the number of coordinates I, such that if you flip this i's coordinate of the vector x, that changes the value of f. So for example, if you take the OR function in n variables, and you consider the all 0 vector, then for all 0 vector as an input, then this function outputs 0. Right? But as soon as you change one of its coordinate from 0 to 1, it outputs 1. So every coordinate is sensitive with respect to this input. So the local sensitivity is just equal to n. So the overall sensitivity is just equal to the maximum local sensitivity of this Boolean function. So in this case, it's also equal to n because this number can never be greater than the number of variables. And similarly, you can show that the n function in n variables has sensitivity equal to n as well. And now you may have realized that both functions have degree equal to n as well. And people in the CS community, they are interested in studying whether these complexity measures are polynomially related to each other. So, and they have shown that, prior to 2019, they proved that a bunch of complexity measures are all polynomially related to each other, meaning that if you have m1 of f less or equal to m2 of f to the c1, greater or equal to m2 of f to the c2. If you take m1, m2 to be two such complexity measures. But the only outlier at that time was the sensitivity conjecture, sensitivity. So Nissan-Szegedy conjectured that sensitivity also belonged to this family. And so for one direction, it was already known long time ago. That's because there was one notion called the Bloch sensitivity that I haven't mentioned. And this is greater or equal to the sensitivity. So you just need to show that the sensitivity is greater or equal to any of these complexity measures to the power of C. And I think, so for example, you can just look at the degree versus the sensitivity. And the reason that I got attracted to this problem is because it has a very nice combinatorial or rather graph theoretic formulation. Gossamer and Linear in 1992, I think that's right after Nissan-Szegedy posed this conjecture. So they proved that the conjecture can be reduced to the following question. So you take an n-dimensional hypercube graph. So basically you have a bunch of n-dimensional binary vectors and you put a vector, you put an edge between two vectors if they differ exactly one coordinate. So now you take this hypercube and you partition the vertex set into two parts. So for example, the red one and the blue one here on this page. Now, suppose this is not a balanced partition, meaning that you don't have exactly half vertices in one part and half the vertices in the other part. Then as long as you can show that if you look at these two induced subgraph, the subgraph induced by the red vertices and the subgraph induced by the blue vertices. So if you can prove that one of them has the maximum degree greater or equal to h of n. So h of n is a function in the dimension of the cube. So if you can do that, then this implies any Boolean function f satisfies the sensitivity is greater or equal to h of its degree. So in particular, if you can show that h of n is equal to n to the c for some strictly positive c, then you can prove this conjecture. So I think one of the reasons that this reformulation was sort of neglected by people over the last 3 decades was because it's not supernatural in the sense that it's very hard to deal with, two different induced subgraphs. So can we just deal with one of them? And the answer is yes. So you can just take, for example, the red vertices. It has strictly more than half of the vertices. And it turns out that we could prove as long as you have strictly more than half of the vertices, then the maximum degree of this induced subgraph is already greater or equal to root n. So, and here I would like to say that previously this approach was actually tried by Huang, Ferretti, Graham, and Simo in 1988. So they were able to show a lower bound of 1/2 times log n. And that corresponds to an upper bound like the, let's see. So the sensitivity, so e to the sensitivity is greater or equal to the degree. Okay. Here I probably messed up with the constants, something like that. So also I'd like to say that this square root of n is best possible. And in the same paper, this group of 4 mathematicians gave a construction with 2 to the n minus 1 plus 1 vertex induced subgraph of the cube, which has maximum degree exactly root n if n is a perfect square. Okay. So basically, the theorem says that if you look at the hypercube, you can find half of the vertices such that they do not span any edge, right? Because you can just take all the odd vectors or all the even vectors. But as long as you have one above that, then the maximum degree suddenly jumps from 0 to root n. And from here, you can use this Gossamer linear reduction and show that the sensitivity is greater or equal to the square root of the degree. And I haven't talked about the construction, but you can sort of sense like how it looks like from the Boolean function that shows this bound is tight. So this is by the so-called N of O function. So basically you write down your variables. So let's say that you have a k by k, k squared variable. So list them as in a matrix form. Then for the first row, you take an OR function. And for second row, you also take an OR function and so on. And then you take an N function of everything. So you can prove that the degree is equal to k squared and the sensitivity is equal to k. So this is sharp. Okay. All right, so the proof is basically motivated from this idea that interlacing can help you understand the structure of an induced subgraph, as long as your host graph is nice enough. So first of all, it's pretty difficult to study the maximum degree of an induced subgraph directly because for example, if you write down the degree sequence, then the maximum degree is like the L infinity norm of that sequence. So I don't know what's the algebraic way to study an L infinity norm. So for example, you can look at the L1 norm. That corresponds to the average degree of your induced subgraph. But unfortunately, this doesn't work for our problem. And that's because if you take the previous example, okay, let's take a three-dimensional cube, for example. So you take all the even vertices. Of course, that gives you an independent set, right? But if you just add one odd vertex, so that only gives you 3 edges in the induced subgraph. So for example, if you have an n-dimensional cube, I think that induced subgraph only has n edges. So the average degree is miserably low. So it's something like n over 2 to the n. Although there exists one vertex which is large degree. So the L1 norm doesn't work here. So can we look at some other type of norms of the degree sequence? And that's why I started to try to use this special technique. And it turns out that the largest eigenvalue is just a good candidate. So you can prove that actually the largest eigenvalue is polynomially related to the largest degree of your graph. And more specifically, it's bounded from above by the maximum degree, and it's bounded from below by square root of the maximum degree. So I think the upper bound appears in most of the standard graph theory textbook. So just take your eigenvector corresponding to the largest eigenvalue, and then you just check this by definition. So multiply the adjacency matrix to this eigenvector, and you apply the triangle inequality. So throughout this proof, essentially you only use that this matrix A has the ij's entry equals 0 if I is not adjacent to J. And if I is adjacent to J, then its absolute value is less or equal to 1. And I think here probably I need to assume that every entries are real numbers, and this is a symmetric matrix. Okay. And we are going to use this later. And for the lower bound, it actually follows from the fact that if you have a graph, then every time when you remove an edge, the largest eigenvalue of the adjacency matrix can only go down. It never goes up. That means if you have a graph whose maximum degree is equal to delta, so you can sort of remove all the other edges not incident to the vertex of the largest degree. So you only have a star together with a bunch of isolated vertices left. And after that, you get this star. And for star, I mean, it's well known that the eigenvalues, there are only 2 non-zero eigenvalues, square root of delta and minus square root of delta. Then you have a bunch of zeros, and the isolated vertices also give you a bunch of zeros. So now the largest eigenvalue of a star is equal to square root of delta. So that gives a lower bound on the largest eigenvalue of the initial graph. Okay, so we know that they're polynomial related. So we really have to show that the largest eigenvalue of this induced subgraph is greater or equal to n to the c in order to establish this sensitivity conjecture theorem via this Gaussian linear reduction. So there's one other benefit of using this interlacing, using these eigenvalues instead of maximum degree, because maximum degree normally do not interlace. Well, I don't even know what interlacing means there. And for eigenvalues, they interlace nicely. So here you have already seen this Cauchy's interlace theorem. So our goal is to lower bound the largest eigenvalue of H, which is a 2 to the n minus 1 plus 1 vertex induced subgraph. So we know if you take an induced subgraph of your large graph, so its adjacency matrix is just the principal submatrix of the large adjacency matrix. So we can apply interlacing, and this has to be greater or equal to, sorry, this is mu, by the way. It's greater or equal to lambda. So here I have to figure out what this index is, but of this q to the n. So basically, this index is equal to 1 plus 2 to the n minus 2 to the n minus 1 plus 1. So if you apply this direction of this Cauchy's interlace theorem, so you end up with 2 to the n minus 1. Okay. But what's the 2 to the n minus 1's largest eigenvalue of the hypercube graph? So we know how to compute the eigenvalues of Qn. So it's basically the same calculation from this earlier result about this m and k. So there are n plus 1 different values, and these are n minus 2, n minus 4, all the way down to minus n. It's a arithmetic progression. And each of them appears with multiplicity n choose I. Okay, so now the 2 to n minus 1's largest eigenvalue is somewhere in the middle. So depending on the parity of n, you get either 0 or 1. So that looks like a terrible bound, right? Because this gives you a lower bound on the largest eigenvalue of h, which is either 0 or 1. So remember our goal was to bound the largest degree of this induced subgraph. But we already know that if you take 2 to the n minus 1 plus 1 vertices, the degree, there exists an edge, right? So the maximum degree is already greater or equal to 1. So this also shows you that the maximum degree is greater or equal to 0 or greater or equal to 1. So it looks like a very weak result. But from here, you can already get that if you have, let's say, a constant proportion more than half, then the maximum degree is greater or equal to c times some root n. That's not too bad. At least we can prove something. And the remaining piece of this puzzle is you can just put the proof of the first lemma. And instead of looking at all these adjacency matrix, you can replace the 1 entries to either +1 or -1, or you can do any real numbers between -1 and +1. And the same lower bound applies, the same bound applies, and you can still use interlacing. So if we can find a pseudo adjacency matrix such that the middle eigenvalue is greater or equal to root n, then we are done. And the reason that I came to this type of approach was basically because if you look back at the previous proof, I think when n is an even number, you have a bunch of zeros in the middle. So that proof does not even give you the independence number of a hypercube, which is supposed to be 2 to the n minus 1, right? Because of these zeros. When you apply this inertial bound, you have to count the number of strictly positive eigenvalues plus the number of zeros, or the number of strictly negative plus the number of zeros. So if you have a bunch of zeros, I think that gives you a bound larger than 2 to the n minus 1. So it turns out that we can actually find such a matrix, and you can take a ±1 pseudo adjacency matrix. Oh, sorry. And the construction is, when I wrote a paper, I put it in a recursive form. But basically, you're looking for a matrix whose square is equal to n times the identity matrix. So that will cause all the eigenvalues to be either square root of n or minus square root of n. And now because the trace is equal to 0, so exactly half of them are root n and half of them are minus root n. So the 2 to the n minus 1's largest eigenvalue has to be exactly root n, and that completes the proof. So after I proved this result, I got many questions regarding the uniqueness of this matrix. And it turns out that basically this is unique. I'll explain what I mean by that in a moment. So this is because by Hadamard's inequality, if you have a matrix and you know the row vectors, then the determinant of this matrix is bounded from above by the product of the lengths of the row vectors. Geometrically speaking, I think it's hard to, so it's not hard to visualize, right? If you take a parallelogram, then this area is bounded from above by the product of these two side lengths. And you can also see from this geometrical interpretation that the equality is achieved if and only if you have these two sides to be parallel to each other, to be perpendicular to each other. Now, for example, if your M is a side adjacency matrix, now because you have this 2 to the n by 2 to the n matrix, and every row has exactly n of the entries being plus or minus 1, and the rest of the entries are 0, then the row vector has length at most square root of n. Now you can just apply this inequality. So the determinant of this matrix is at most root n to the power of 2 to the n. And on the other hand, if you want your 2 to the n minus 1's largest eigenvalue to be at least root n. So basically, because the hypercube is a bipartite graph, so you have half of the eigenvalue to be greater or equal to 0, and half of them to be less or equal to 0. So if you want the middle ones to be greater or equal to root n, so the next one has to be less or equal to minus root n. So all the first half has to be greater or equal to root n, and all the second half has to be less or equal to minus root n. So the product gives you the determinant, which is absolute value at least root n to the 2 to the n. So you really need this to be equal because of these two inequalities. And it turns out that the only possibility is you have n transpose times m is equal to n times I. And from there, it's not hard to obtain the actual matrix. And when I say this is unique, it means, so for example, if you build this matrix as a signing on a hypercube, so you have, for example, the two-dimensional case correspond to such a signing plus, plus, plus on 3 edges and minus on the last edge. Then you see you can always fix a vertex and change the sign of these two edges incident to it. So that's not going to affect the spectrum of this adjacency matrix. So up to that operation, this signing is unique, for our purpose. Okay, so I have a lot of time, so let me conclude my talk with one of my favorite questions. It's in discrete geometry, but I always have the feeling that maybe some techniques from spectral graph theory could be useful there. So this was a conjecture by Kushner in 1983. So if you take the n-dimensional Euclidean space, and you want to make sure that their pairwise L1 distances are all equal to, let's say, 2, then there are at most 2 times n such points. And the way to achieve 2 times n is, for example, in the one-dimensional case, that's easy. So you can take at most 2 points. For the two-dimensional case, you can take these 4 points on the vertices of a diamond. And then for higher dimensional cases, you can take a cross polytope. So this conjecture is basically wide open. So for this particular case, so okay, you can of course consider this for LP distance. So this corresponds to P equals 1. So the best bar was done by Arlong and Pudlak, and something like constant times n log m only. So it's still, it's not even linear in n. And there are also some other nice results. For example, if you consider the normal Euclidean distance, so you can take at most n plus 1 points. You can take the vertices of a regular simplex. And P is equal to infinity is 2 to the n. Actually, for any P, 2 to the n is upper bound. And for some other range of P, you can get some nice result. But the most interesting result is when P is equal to 4. So if you consider the L4 distances, you can take at most n plus 1. And okay. So I don't know, so you can formulate this as an independence number for finite, for many different finite graphs. If you can solve the each of them as independence number at most 2 times n, then you are done. But although I don't know how difficult it is and whether the strength of this spectral method is enough here. Okay, so let me stop my talk here and thanks for coming.
Well, thank you, Hao, very much. It's a very interesting talk. So let's see if we get some questions from the audience. We'll just wait for a few minutes until the questions come in. For a few seconds.
Maybe I could ask a kind of naive question. So I read your proof of this sensitivity conjecture, which was very, very beautiful. And you know, this pseudo adjacency matrix, I guess you can write it as a sum of n of the generators of a Clifford algebra. Mm-hmm. And so this fact that you stated that, you know, this matrix M is unique, I guess it's a fact about when you have a representation of a Clifford algebra where all the generators are, you know, signed adjacency matrices. Is that right? Is that how I should interpret that?
To be honest, I admit that I'm not super familiar with the language of Clifford algebra, but I believe some have statement like that. Yeah.
Thanks.
I think there have been some discussions online about this. Yeah. So let me tell you a different problem. So if you look at 3 to the n instead, so the cube is like 2 to the n. Mm-hmm. Look at 3 to the n in the same way. Okay. So basically, the Hamming distance is like if you have, let's say, a coordinate equals 1 and the other equals to 2, then the Hamming distance is 1. Okay. So now you know the independence number is 3 to the n minus 1. But what do you think will happen if you take 3 to the n minus 1 plus 1 vertices? So the answer is no longer constant times root n. So you can actually find a way of choosing this many vertices such that the maximum degree is only equal to 1. That means it's a perfect match. Yeah. I think it's interesting. I would like to see from the algebraic perspective what this says. So, there's probably a nice explanation of that. Yeah, but maybe if you go sufficiently high, then you still get root n. I mean, that means true, but maybe here you can replace it by something else.
Thanks, that's very interesting.
Okay, other questions? Okay, so I think
I have a short comment. Sorry, I have a short comment on the uniqueness. The uniqueness of this signing was actually first proved by Cohen and Teets, and I've forgotten the year, but it was some time ago. And in fact, if you view what's going on graph theoretically, there's a fairly simple proof. And so I used to sign it as an exercise in my algebraic graph theory course, and a good fraction of students solved it, so you can prove uniqueness. And they were innocent of any knowledge of Clifford algebras, as was I.
Thanks.
So the point is there are a number of interpretations, and so you can interpret those Clifford algebras and get uniqueness proof, but there are other ways of looking at it.
Thank you, Chris. Any other questions or comments? So I think we will leave more discussions in informal discussions after I switch off the recording. So let's unmute ourselves and thank Huang Hao for such an interesting talk.
Yeah, probably let me disable my screen sharing. Okay, see.